Okay, any questions for you, bro? All right. Well, so here's some kind of number theoretic properties of the integers we talked about last time. The first one says, suppose A and N are relatively prime, they've got no factors in common, and suppose X and Y are the same mod phi to the n. So X minus Y is divisible by phi to the n, where this is the Euler phi function. Remember, that counts the number of elements between 1 and n that are relatively prime to n. Then A to the X power is equivalent to A to the Y power mod n. We'll make the distinction between mod n and mod phi of n. This is actually, proofs are useful because these proofs are very computational. They show you why this stuff works. Wilson's theorem, if n is a natural number that's bigger than 1, then it's prime if and only if n minus 1 factorial is equivalent to minus 1 mod n. And finally, Fermat's little theorem, if p does not divide a, then a to the p minus 1 is equivalent to 1 mod p. This is a bit of magic. We did an example last time. I think I took, well, I forget what the example was that I used. I think I took 2 to the 12th power. I took p to the 13. My 2 to the 12th power is equivalent to 1 mod 13. So why does this all work? And like I said, in particular, number 3 is used a lot in coding, for example. We'll see some applications of this later. Okay, so let's kind of take apart what everything is. So what do I know? I know the greatest common divisor of A and N is 1, so it's got no factors in common other than 1. And X is equivalent to Y mod phi of n. Okay. Well, let me write down what that means. Remember, what it means for X and Y to be the same mod phi of n is their difference is divisible by phi of n. Agree? Now, let me also point out that if we consider Cn, so I want to couch this proof in terms of looking at Cn. Every element is a unit or right? You guys remember that. And remember, how do you test this in Z mod n? You look at all the element, you look at the element, and if it's got a common factor with n, then it's a 0 divisor. And if it's relatively prime, then it's a unit. Everybody remember that? So what does this mean? The number of units right, because phi of n actually counts the stuff that's relatively prime to n, right? And so the number of units, that phi of n tells you the exact number of units. Everybody agree with that? And units of Zn form under multiplication. So here it is, one of our first practical applications of groups. Let me verify this is true. Suppose what does it mean for AB to be units? It means there exists UV in Zn with a U is 1 bar PV, right? That's what it means to be a unit. You can multiply it by something, you get 1 bar. Everybody agree with that? Okay, what do you gotta, somebody remind me, what do we gotta have to be a group? We've got to have several things. It has to be closed. Okay, so A and B are both units. Is A B a unit? Did anybody see what I can multiply AB by to get 1 bar? Okay, there you go. So it's closed. The product of any 2 units, A and B, is a unit. Okay, what else we gotta have? We gotta have that annoying associativity, right? But multiplication is associative, so I'm gonna wave my hands at that. Okay. Anybody remember the 2 other things we need for a group? Every element's got an inverse, and also you got to have an identity. Anybody know what the identity element would be? What can you multiply by anything that leaves it alone? Right. And let me point out that 1 bar is a unit also, because 1 bar times 1 bar is 1 bar. Everybody agree with that? And finally, inverse. And there's your inverse. Everybody agree with that? And remember, the identity here is the 1 bar, right? This group is of size phi of n. Right, because that's the number of things that are relatively prime to 1. Now, what does Lagrange's theorem tell us? What do we know about the order of A?
It divides the order of.
It divides the entire order of the group, which is in this case phi of n, right? It's in this case phi of n. So we're almost done with this now, because notice. Oops. Now remember, X is Y plus K becomes phi of n. Phi of n. Everybody okay with that? A to the X power is A to the Y power, K phi of n. This is A to the Y power times A to the phi n K power. Everybody okay with that? And what's A to the phi n power? Well, the order of A divides the order of the group, right? So suppose the order of A is Q, right? That means A to the Q is 1, and this is a multiple of A, or this is a power of A to the Q, so it's a power of 1. This is 1 bar to the K power. So in Zn, a to the x power is a to this y plus k phi n power. But a to the phi n power, phi n's the order of the group, that's automatically the identity. Because remember, the order of the element is the smallest integer for which that power gets you 1. So this is a to the y and c to the n. So a to the x, a to the y. That's the first statement. Yes.
Could you please explain again why the number of units is exactly phi to the n or phi n?
Because what phi n counts is everything between 1 and n, or the same thing, everything between 0 and n minus 1, that is relatively prime to n.
Oh, okay.
And those are exactly what the units are.
Okay, yeah.
Other questions? Okay, how about Wilson's theorem? Well, the first thing for Wilson's theorem that I want to point out is for number 2, consider Cn again. Okay, let me point out that that x, let's see, which way do we want to do it here? Right, suppose first that x is, I'm going to suppose first that n is prime. And of course, what I want to do is show n minus 1 factorial is equivalent to -1. Okay, let me point out, I need to make a quick observation. X is in Zn, not 0 bar, and x is a unit. Because count between 1 and, in this case, n is prime, between 1 and n, how many of those elements are relatively prime to the prime n? All of them except n, right? So everything that's not the same as 0 bar, all the other n minus 1 elements must be n's. Everybody agree with that? Because they can't share a factor with n. That does depend very heavily on this being prime. Suppose x is a unit and x squared is equal to 1. That is, suppose you have something that squares 1. I can think of 2 things maybe that square 1, namely 1 and -1. But it occurs to me, could there be other things that square 1? Certainly there are mathematical structures where there are infinitely many things that square 1. Look at matrices. I can give you infinitely many things that you can square to the identity. Okay, but here, those are the only possible solutions. This means that x squared minus 1 is 0, which is x plus 1, x minus. So if x is not equal to plus or minus 1, then 1 is a 0 divisor. If neither of these are 1, then it has to be a 0 divisor because you got because what that means is these would be 2 non-zero things and multiplied to be 0, right? Everybody agree with that? And that's not possible. So x equals plus or minus 1 are only possible solutions. Okay, now I'm ready to finish this off. Actually, I've got a degenerate case. Case 1. N equals 2. The oddest prime of all, right? Remember, I'm assuming that n is prime, so let me just do this first. Then n minus 1 factorial is equal to 1. I agree with that. Which is equivalent to minus 1 mod 2. 1 and minus 1 have no distinction, mod 2, they're the same thing, right? So Wilson's theorem holds here for n equals 2. Case 2, odd prime. Well, let's look at n minus 1 factorial. N minus 1, n minus 2. 3, blah, blah, 3. Now, let me point out that 1 is its own inverse, right? X squared equals 1, so it's its own inverse. Everybody agree with that? And that is also its own inverse, because that's the same thing as negative 1. N minus 1 is equivalent to minus 1 mod n. Everybody agree with that? How many elements are left over? Well, n was odd, right? So this list right here should be an even list, right? 1, 2, well, let's count the smart way. 1, 2, 3, up to n minus 1. If n is odd, there's an even number of factors in this factorial. Agreed? Now, I throw out the 2 in yellow because they're their own inverses. And now I've still got an even number. Everybody agree? Now, these are all units, right? So they all have an inverse. Everybody agree with that? That's what it means to be a unit. Every one of those things in that white list in the middle has something that multiplies it and gives it 1, right? None of them are their own inverse because of this. So they all have different inverses other than themselves, right? And since there's an even number of them, the inverses pair off. So if these pair off in inverses, what is this entire product? I'll multiply this whole thing on white together. It should be 1 because everything has an inverse in there. They all pair off, you get a bunch of 1s. Agree? This is a big fat 1. That's a 1, and that's negative 1. It's a nice little observation, right? Because again, I've used group theory here because everything has an inverse and they have to pair off. Any questions on that?
Why is n minus 1 its own inverse?
Because it's the same thing as minus 1.
But isn't, so I thought 1 was the,
Well, so let's just brute force this. Square that. Right? Which is equivalent to 1 mod n, because this is divisible by n. Right? That means that n minus 1 times n minus 1 is equivalent to 1 mod n. So n minus 1 is the
okay.
Everybody okay with that? Now we've got another direction for Wilson's theorem to go. And the other direction is, now let's assume, so we have to prove this direction here. And that is to say that this implies this. So suppose so what we're going to do is we're going to do the contraposit. We're going to assume that n is not prime and show that this is not possible. one of at least one of these has to be a zero divisor if n is not prime, because one of these has to have a factor in common with n. Because, for example, if n is a times b, a is less than, and a is somewhere in this list, agreed? So it has to have a zero divisor in there somewhere. So 1 times 2 times 3, n minus 2, n minus 1 cannot be a unit. Because if any one of these is a zero divisor, then the whole product has to be a zero divisor. And of course, minus 1 is always a unit. So this gives here. Everybody okay with it? Any questions? By the way, do you all see why this is true? That if you have, if even one of these elements in this product is a zero divisor, the product can't be a unit, so it can't be -1, which is always a unit. Do I see why that's true? Maybe I should share that real quick as a sign here. Suppose Z is a zero divisor. So there exists A not zero such that AZ equals. Now suppose that RZ is a unit. Suppose that there's a zero divisor and I multiply it by something else that's a unit. Well, this means there exists U such that URZ is 1. Now, let's multiply both sides. Let's multiply both sides by A and rearrange things. But notice that A times Z is equal to 0. And ordinal multiplication here doesn't matter. So I get 0 on this side and I get A on this side. That's a contradiction because we assume that A is not 0. Right. So it's impossible to be a multiple of the zero divisor also. Any questions on that? Okay, finally, how about our little coding theory friend here? Fermat's little theory. So we want to show that if P doesn't divide A, then A to the P minus 1 is equivalent to 1 minus B. Well, suppose A is in CP and A is not equal to 0 bar. Then, as we've observed before, the non-zero elements of C mod P, 1 bar, 2 bar, whole way up to P minus 1 bar, they form a group under multiplication, right? You've already seen that because everything there is relatively prime to P. And A is in here somewhere, right? Notice that by Lagrange's theorem, the order of A divides, we'll call it something M, divides P minus. Everybody agree with that? So that is to say that P minus 1 is MK. Okie dokie so far? So let's look at A to the P minus 1. This is A to the MK, which is A to the M, okay, which is 1 bar. So A to the P minus 1 in ZP is always equal to 1 bar. And an interpretation of this in the way that I've stated it here is A to the P minus 1 is equal to 1 mod P. So the group theory actually makes this a lot easier than kind of slogging through it from first principles. Any questions? I'm going to make one more remark here before we start talking about the Chinese remainder theorem, which I promised you earlier. You can actually capture Fermat's little theorem in a more sweeping sort of context. What Fermat's little theorem says is if A is not divisible by P, then A to that P minus 1 power is equivalent to 1 mod P, right? Next question, what if P does divide A, right? If P does divide A, no way is this happening. Because if P divides A, then A is equivalent to the 0 bar in Z mod P, right? No power of that is ever going to be 1. Agree? No power of the 0 bar is ever going to be 1. Agree? But you could write it this way. Notice this captures everything. Because if A is divisible by P, then this is certainly true because this equation basically says 0 bar to the P power is 0 bar, right? And if P is relatively prime to, if A and P are relatively prime, you can think of multiplying this equation by A inverse because if A and P are relatively prime, then A is a unit and you recover this equation, right? So this gets everything. This one, you have to have the A and P are relatively prime. This one, it works for every A. So if you take any integer, well, 8675309 is in fact a prime. If you take 17 to the 8675309, 17 to that power, it will be equivalent to 17 mod 8675309. Okay. Any questions before we move on? Okay. Here is a very powerful theorem, and this one's actually very powerful. I'm going to state it to you this. I'm going to state it to you in terms of solutions to equations, and then when we talk about rings very shortly, I'm going to state this to you again in another context. It will be equivalent, but it'll be nice to be able to use both of them. It makes you more versatile. So I'll tell you a fairy tale here, because this may be true and it may not be. But the story I always heard about this is that some of the old Chinese generals, I guess maybe some of the Chinese mathematicians taught them how to do this, had this trick for counting the soldiers in their armies, right? Because, you know, you want to know how many people you've got in your army before you go into battle. And who knows, people that have gone off their AWOL or got killed in the last battle. How do you know how many people you've got? So let me start you with an example and we'll work through this. Here's a motivating example. An army starts a battle with 30,000 troops. Troops. There we go. And after the battle's over, right? Maybe the general wants to attack again, but it's very important to know how many troops are left. If you've got 10 folks left, bad idea attacking the Reavers now, right? So. Assess how many are left. So here's the trick the general used. So I'm going to do this in terms of squares because, you know, maybe we can imagine that these are all troops. So nobody wants to count this, right? I mean, unless it was a terrible, terrible battle, I would expect there's probably at least 10,000 left over, right? Nobody wants to count that. So let's see what we got. So what the general does is he makes the troops organize into groups of 81, right? 9 by 9, right? So maybe this is something they do in drills. They quickly organize in squares of 81. In square formations. And they do this 3 times. They get in square formations of size 81, and they find quickly that there are 10 stragglers left over. So there's a certain number of these squares filled, and there's 10 left over when they start. Then they organize in groups of 25. And there's 1 left over. And then they organize in groups of 16, and there's 1 left over. In both cases. Now, with this, so they get in squares 81, they say, oh, we got 10 guys left over. There's 10 that don't fit in the blocks. And get in 25, oh, there's 1 left over. 16, okay, there's 1 left over. All right. Now, just with this information, I can tell you how many tricks they have, which is really kind of amazing. Now let's see. I want you all to help me with this. So how is this information going to give us how many troops there are? Oh, and there are 2 things I know. Somebody give me some naive assessment that we can make about the number of troops going in.
Going to be less than 30,000.
Yes, that is correct. That is that's an important assessment. Number of troops. I assume, we'll pretty quickly find if everybody's dead, right? So there's no zombies, so there's at least there's 0 or more troops left over, and there's no more than 30,000, right? So how are we going to do this? The first piece of information means number of troops. Well, can somebody interpret this? So from this, for example, somebody tell me why in groups of 81 with 10 troops left over, I know that there is not 80, it's impossible for there to be exactly 80 soldiers left. In fact, this narrows down your numbers quite a bit, because what does this piece of information tell you? Well, let's think about this. What do we know about our troops? They're all in blocks of 81. I don't know how many blocks there are. And then there's 10 left over. Right? Everybody agree with it? So I can just start listing possibilities here, and let me do so. So there could be 10, there could be 91, there could be 172, there can be 253, there can be 334. Okay, this is getting tiresome, right? But at least there's, I think you'd have to agree that we've eliminated an enormous number of possibilities at this juncture. Everybody agree with that? But still, I don't want to go up to 30,000 like this, right? I mean, it took me 5 just to get to here, and 30,000, roughly, I'm gonna have to go about 100 times. I don't want to list 500 numbers. Nobody wants that. So how can I make my life a little bit easier? Well, I've got 2 other pieces of information that I haven't used. Let me go over a few more steps of this, just because it might sort of help jog the brain pan a little bit. Keep adding 81. This is 415. This is 496. This is right like that.
0, 1, 2, 3, 4, 5, 6.
Right, so we also know that the number of troops is also equal to 1 plus 25 L, right? So when I subtract 1 from this, is it divisible by 25? No way. Everybody agree with that? This one's a little bit closer because at least it's divisible by 5 when I subtract 1 from it. It's still not divisible by 25, right? This is divisible by no way when I subtract 1. Where do my possibilities come up? 4 or a 6. Everybody agree with that? So we can narrow down. So the second condition allows us to narrow down. I'm going to narrow down a number of times. 91. I said I'm going to just go with the possibilities that sort of work, the 1 or 6 possibilities. 496. How much did I jump to get from there to there? 405, right? And 405, notice is multiple of 81 times 5. Another 405 would be a 1. I guess that'd be 901. Now, notice if you subtract 1 from this, is it divisible by 25? How about the next one? If I do 405, 1306. Anybody want to guess? So here's the first opportunity, 901. Everybody agree that 901 satisfies this and this. Does it satisfy this? $900, I think, is divisible by 4, but not 16, right? So it doesn't work for this. So where's my next opportunity going to come? What do you suppose I have to add? Or what do you suppose I jump by now to get to the next chance that this might work? Well, let's see, I mean, let's do the 405s for a bit. This is 1711. This is 2116. Now notice when I subtract 1 from this, yeah, there's no way when I subtract 1 from this, it's going to be divisible by 16. It's going to be odd. So 1711, that's a possibility. But 170, when I subtract 1, 1710 doesn't have enough factors 2 in it. Okay, so instead of jumping, so I'll now ignore this, right? The 405s, because I really just need to add 810, right? Because it has to end in an odd to subtract 1 and be what? 16. So this was 810. Let's do another 810. Leapfrog this. This is 2521. Is that divisible by 16? No, it's not. But let me point out also that the rest of this is overkill, right? Because notice what we have so far is the first time is we jumped 81. And now, every time we jump 81, it keeps that okay. But we also have to now jump by steps of 25, right? To make sure that we keep the second thing okay, right? And so if you're going to jump by 81 every time, you also need to jump by 25. 81 and 25 are relatively prime. So to do a jump that is a multiple of 81 and a multiple of 25, it has to be a multiple of the product, right? And what's 81 times 25? Somebody help me, I guess it's 2025, I guess. You should probably check me on that. Let's see. Yeah, that's right. And notice that's, what do we jump by? 2025? And obviously I did this wrong. Let's see. Right, so that should be. Oh, no, I did it right. So the next jump is, so here are our possibilities that incorporate them all. 901. I jump by 2025. I get 2926. But see, again, there's no way that that's going to be divisible by 16. Everybody agree with that? Because when you subtract 1, that's going to be an odd. So actually you can jump by you can actually jump by 405, right? So actually, because when I jump by 2025, every other one is going to end in 6, and there's no way when I subtract 1, it's going to be divisible by 16. So let's jump by 405. So this is 4951. That's going to be 01. 9001. Is 9001 divisible by, or 9001 minus 1 is divisible by 16? Yeah, Lucas, you're going to keep me honest on this, aren't you?
Wait, so what was it?
Do you? I thought you had a calculator. Do you?
I'm like trying to just do some like modular arithmetic stuff just to make sure I'm doing it right now on my phone.
So let's jump another 405. 405 on it, 13051. When I subtract 1, it's not divisible by 16. 4050 is 17101. When I subtract 1, it is 100. That's not divisible by 16. 4050, this is 21, right? 151. That one is not, when I subtract 1, it's not divisible by 16. 4050 again is 25 201. Aha. When I subtract one from this, divide by 16 is 192. That's going to be 60 times 5. Yeah, this was about 16. And so notice this is the first time in the interval well, smallest number that satisfies one, smallest number n that satisfies n is 10 plus 81k. 2 n is 125k. Let me call k 1, 2, and 3 n plus 16. Yes.
Like, is there like an easier way to solve this? I guess other than like writing it down, like using like matrices or something, or like.
You can do this, and actually, I even give you the Chinese remainder theorem.
Yeah.
Right, and yes, I can show you how to solve this in an easier way.
Yeah.
Usually, you start with the biggest modulus. I sort of try to do this from first principles and trying to figure out kind of a pattern. This example that we worked through here basically contains the seeds of the proof of the Chinese remainder theorem. Notice that we have now figured out there are 25,201 proofs left. Now, you may think that's a pain in the butt, what we did, but let me point this out. Let's suppose that you have this battle-weary army in front of you, and you go through and count them head by head, or have them call off the numbers, right? First of all, you've got to get them organized because you've got 7 guys all yelling 2 now, if you ask them to count off numbers. Well, let's suppose that you have them count off numbers and they can do it in an organized fashion. And suppose that they can count 1 person per second. It will take you 7 hours and 1 second to count that many troops. Whereas basically using this mathematics and first principles, we got it in 7 minutes. Okay, basically 60 times faster. Okay, any questions? Let me state the Chinese remainder theorem so you guys can cogitate that for next time. So here's the formal statement. Well, one of the formal statements that we'll give. I'll use that. If you see CRT, I mean that. I don't mean critical race theory, so don't put that on YouTube or anything. I mean Chinese remainder theory. Suppose that M1 into in K is a collection of pairwise relatively prime features, and we'll say that each n is greater than 2. No more 1 there. It'd be kind of silly. And let n in the product. So n is what you get when you multiply all these out. Capital N is. Then the system of congruences. And that's exactly what we did here is we solved the system of congruences. Congruences. X is equivalent to A1 mod N1 X is equivalent to A2 mod N2, all the way down to X is equivalent to AK mod NK, has a unique solution, Z. Zero and capital N minus one. And here in the example that we did, my N1 was 81, my N2 was 25, and my N3 was 16. And that has a unique solution mod. Well, this has a unique solution up to the product of these three minus one, which 16 times 25 is 400. So that's like 32,400. So that 25,201 that we got here, that's the only solution if you restrict between 0 and 32,399. Okay, that's a good place to stop. Think about that. Think about how that ties into our example, and we'll move on with this on Friday. Any questions? Any questions? All right. Well, you all have a good one, and we will see you next time.